Okay. Good afternoon, students. So, welcome to physics online live classes. So, today we have lecture number 3. Lecture number 3 on electric charge and fields. Okay. In the previous class, we have studied about the electric field intensity. In the previous class, we have studied about electric field intensity, and before that, we have studied about Coulomb's law, and then we have studied permittivity, relative permittivity, that is called dielectric constant, and all the things we have studied. Electric charge, properties of electric charge. So these all are the concept which we have studied in the previous classes, and then we have studied electric field and electric field intensity. Electric field intensity. Electric field intensity. So what is electric field intensity? Electric field, once again I will tell what is electric field intensity. Electric field intensity is defined as the electric field intensity at a point in an electric field. Electric field intensity at a point in an electric field is defined as the force experienced by a unit positive charge at that point. Force experienced per unit positive charge at that point is called as electric field intensity. That is given by, denoted by E, and given by the formula E is equal to F divided by Q naught. And electric field intensity, the SI unit of electric field intensity is Newton per Coulomb or volt per meter. And dimensional formula of electric field intensity is dimensional formula of force is M-L T to the power minus 2. Dimensional formula of charge is AT. So you will get M-L T to the power. This one goes to numerator, T to the power minus 3 and A to the power minus 1. So this is dimensional formula of electric field intensity. That's unit. And then we have derived the electric field intensity due to an isolated point charge. So if there is only one point charge, that is one source charge, we have said it is a plus Q, or a charge Q is producing an electric field. That is the reason around the charge Q where another test charge will experience as the force. That reason is called electric field. If the charge capital Q is producing the electric field, then capital Q is called as the source charge. Capital Q is called as the source charge, and in the electric field of the source charge, another test charge Q naught will experience as a force. And we have taken a point P, and at the point P, the distance of the point P from the point O, or from the place where the source charge is placed, that is R, then we have derived that equation, vector E is equal to F divided by Q naught, and F is force between these two, and force between these two is repulsive because it is also positive, it is also positive. So then you got the formula, that formula as E is equal to 1 by 4 pi epsilon naught Q divided by R square into R cap. Like this you got the formula. You remember yesterday, electric field intensity due to an isolated point charge in the air medium, in the air or vacuum. In air or vacuum is given by 1 by 4 pi epsilon Q divided by R square into R cap. And electric field intensity is a vector quantity. Remember that. Electric field intensity is a vector quantity. That means it has both magnitude and direction. We observe that the electric field intensity, the magnitude of the electric field intensity is directly proportional to the electric field intensity is directly proportional to the amount of source charge. The electric field intensity depends upon the amount of source charge, or how much the source charge is there. So electric field intensity depends upon the source charge, and also depends upon the square, inversely proportional to, or inversely related to square of the distance of the point from the source charge. If the point P is very close to the source charge, then electric field intensity will be more because R value will be less. R value is less, electric field intensity will be more, inversely proportional. Understood? So that means electric field intensity depends upon the source charge, as well as on the distance. And electric field intensity does not depends upon the test charge. Remember that electric field intensity at a place or at a point does not depends upon the test charge. The test charge will not affect the electric field intensity, or it does not affect the electric field of the source charge. So test charge is only used to detect the force. Only it is used to detect the whether there is electric field is there or not. To detect that, this test charge is used. Understood? So electric field intensity depends upon the source charge and also depends upon the inversely proportional to the square of the distance from the source charge. So if the point P is closer to the charge, then the electric field intensity here it will be more and here it will be less. Compared to this point, here electric field intensity will be much more because the distance is very less. As the distance is less, electric field intensity will be more. Understood? If the distance remains same, the electric field intensity will remain same. If the distance remains same, electric field intensity remains same. So if you draw a line like this, circular line from the source charge capital Q, then all the points on that circular line, all the points will have same electric field intensity due to a single source charge. If the source charge is considered to be at the center of the circle and all the points are on the circumference of that circle, then at this point, the electric field intensity will remain same because the distance r is also same and the source charge, the charge which is producing the electric field intensity is also same and the medium is also same. Understood? Okay. So now, and this electric field intensity is a vector quantity. That means it has a direction. And the direction of the electric field intensity is same as the direction in which the test charge will experience the force. The direction in which the test charge will experience the force, in that direction, the electric field intensity will be there. Remember that. The direction of the electric field intensity is same as the direction of the force experienced by the test charge. Here, this is a positive charge. Source charge is a positive charge and test charge is always positive charge. You know that. Test charge is always plus 1 coulomb. It is fixed. Test charge is always unit coulomb. That is plus 1 coulomb. Okay. So now, this positive charge will experience as a repulsive force. That is, force will be outward. The force will be outward or towards the charge. Outward, because this is also positive, this is also positive, repel each other. So therefore, the force will be outward. So electric field intensity, the direction of the electric field intensity is outward. The direction of the electric field intensity is outward due to a plus Q charge. Okay. Due to a positive source charge. And now, if the source charge is negative, let us say, if the source charge is negative, what about now? If the source charge is negative, then test charge is always positive. Test charge is always positive. That is, Q naught is equal to plus 1 coulomb. This is positive charge, this is negative charge. Then they will attract each other. The test charge will experience a force in this direction. Therefore, electric field intensity will be towards the negative charge. The electric field intensity will be inward. The electric field intensity is inward for the negative source charge, whereas electric field intensity is outward for a positive source charge. Understood? So this is about the direction of the electric field intensity. Hope you understood. Electric field intensity is a vector quantity, so it will have magnitude and direction. Magnitude of the electric field intensity depends upon the source charge, amount of the source charge, and also depends upon the distance between the source charge and point, and also depends upon the medium. If there is any other dielectric medium, then the value will become 1 by 4 pi epsilon naught into epsilon r q divided by r square. So that also depends upon the medium. Understood? Okay. So now, next concept. So now, this formula can also be written like this. Some of the books will write like this, then don't get confused. This r cap is nothing but unit vector. R cap is nothing but unit vector in the direction of the force. The r cap is nothing but unit vector in the direction of the force or away from OP or along the line OP. Correct? This r cap can be written as, unit vector can be written as vector divided by magnitude of that vector. vector divided by magnitude of that vector. So therefore, this formula can also be written as vector E is equal to 1 by 4 pi epsilon naught q vector r divided by vector r cube, or magnitude of the vector r cube. Like this also you can write r cube. It is vector r divided by r cube. So one r cancel. Once again it will get r square only. No problem. So like this you can write. Understood? This is in vector form. Electric field intensity in a vector form. Let us say this is electric field intensity in vector form. This is also in vector form only. Okay. So hope you understood about the electric field intensity. So electric field intensity only depends upon the source charge and also depends upon the distance between the source charge and a point. And electric field intensity does not depend upon the test charge. And electric field intensity is also called as, it is also called as electric field strength. It is also called as electric field strength. It is also called as electric field, generally just electric field or electric field vector. Electric field vector also it is called. Okay, and always it is denoted by capital E. Okay. So now next concept. Now to represent this electric field intensity, to represent the electric field intensity, the Faraday has developed a pictorial representation. A pictorial representation for the electric field intensity was required. The scientist Faraday has found that there is a need of representing electric field intensity pictorially or picturally. So therefore, he has introduced the concept called electric field lines. He has introduced the concept called electric field lines. So what are electric field lines? Electric field lines. Magnetic field lines. Have you heard of magnetic field lines? Like that, this electric field lines. What are electric field lines? Electric field lines are imaginary lines. Electric field lines are imaginary lines which are used to represent electric field intensity in space. The electric field lines are imaginary lines which are used to represent electric field intensity. And the tangent drawn to these electric field lines, the tangent drawn to the electric field lines gives the direction of the electric field intensity at that point. Remember that. Electric field intensity are the imaginary lines which are used to represent electric field intensity pictorially. And electric field lines are imaginary, but electric field intensity is not imaginary. Electric field intensity is real. Electric field intensity is real. Understood? Physical quantity. But electric field lines are imaginary. Like this, we can represent the electric field lines. Okay. So, and a tangent, if a tangent is drawn to the electric field line at any point, if a tangent is drawn to the electric field line at any point, then that tangent will give the direction of the electric field intensity. Understood? Okay. So let us understand properties of the electric field lines. Very, very important. Properties of electric field lines. This is very, very important. Many times they have asked in the question paper. Open the question paper, you will understand. Write the properties of electric field lines. Okay. First one. Okay. So electric field lines originate from the or starts from the positive charge. Originate from the positive charge and terminate on a negative charge. Electric field lines originate from the positive charge and terminate on a negative charge. First property. Do you understood what are electric field lines? Electric field lines are the imaginary lines which are used to represent electric field intensity. And a tangent drawn to the electric field lines gives the direction of the electric field intensity at that point. Okay. First property, I'm telling properties of the electric field lines. First one, electric field lines start from the positive charge and end on the negative charge. For example, here. So about these diagrams, I'll tell later. Okay. Second one, electric field lines are imaginary lines. Electric field lines are imaginary lines, but they represent electric field intensity which is not imaginary, which is real. The electric field intensity are imaginary lines, but they are used to represent a real concept called electric field intensity. Third one, a tangent drawn to the electric field line. A tangent drawn to the electric field line at any point gives the direction of the electric field intensity at that point. A tangent drawn to the electric field line. A tangent drawn to the electric field line at any point gives the direction of the electric field intensity at that point. So see here. Okay, I will tell about this diagram. This is plus Q charge and this is minus Q charge. Two equal and opposite charges. Two equal and opposite charges. It is magnitude of the plus Q charge is equal to magnitude of the minus Q charge. Magnitude of the plus Q charge and magnitude of the minus Q charges are equal, and they are placed like this over a certain distance. So now the electric field lines originate from the positive charge and terminate on the negative charge. Like in the magnet also you will draw the magnetic field lines. At the high school level we have studied. So similarly, you can draw the electric field lines. So all these lines represent electric field intensity. All these lines represent electric field lines, field intensity. And now this is the electric field line. And now let us draw a tangent to this electric field line at a point. Let us say this is a point P. If a tangent is drawn to the electric field line at a point, then the tangent will give you the direction of the electric field intensity at that point. The tangent will give you the direction of the electric field intensity at that point. Let us say, draw a tangent to this one. It is like this. Tangent means, a straight line touching only at one point. A straight line touching only at one point to a curved line. A straight line drawn to the curved line touching only at one point. That is called as tangent. Okay, now we will draw a tangent to this electric field line. So this tangent is in this direction, and this will give you the direction of the electric field intensity. A tangent drawn to the electric field lines gives the direction of the electric field intensity at that point. Okay. First point, what is the first property? Electric field lines start from the positive charge and terminate on negative charge. Second point, electric field lines are imaginary lines, but they are used to represent electric field intensity which is not imaginary, that is real. And third one, a tangent drawn to the electric field intensity gives the direction of the electric field intensity at that point. A tangent drawn to the electric field lines gives the direction of the electric field intensity at that point. Fourth one, two electric field lines do not cross each other. Two electric field lines do not cross each other. Do not cross each other. So they will not cross each other. Cross each other. Or they will not overlap on each other. Why? If two electric field lines cross each other, let us say two electric field lines are crossing like this. Then if a tangent is drawn at that point, then there will be two tangents. One tangent is for this curved line, another tangent is for this curved line. So two tangents, so there will be two directions for the electric field intensity, which is not possible. There will not be two directions for the electric field intensity, only one direction. So therefore, two electric field lines will not cross each other. So two electric field lines do not cross each other. Understood? And next, electric field lines do not form closed loops. Electric field lines do not form closed loops. They will not form the closed loop. Electric field lines, two electric field lines do not cross each other, and electric field lines do not form the closed loops. Second point. Next point. Next point. Electric field lines are not allowed to pass through a conductor. The electric field lines are not allowed to pass through a conductor. That is, they will not enter into a conductor because the electric field inside the conductor is not there. It is inside the conductor there is no electric field intensity. It is electric field lines are not allowed to pass through a conductor. The electric field lines are not allowed to pass through a conductor because inside the conductor there will not be any electric field intensity. Electric field lines passes through the insulators or dielectrics. Electric field lines passes through the insulators or dielectrics. Insulators are also called as dielectrics. Okay, so here electric field lines are not allowed to pass through a conductor, but electric field lines are passes through a insulator or dielectric. Understood? These are the some properties. Further, next another one you can write. Electric field lines are always drawn perpendicular to a charged body. So let us say this is a charged body, positively charged body. Then electric field lines are drawn perpendicular to this charged surface. Electric field lines are drawn perpendicular to the charged surface like this. So this is electric field lines due to an isolated point charge. So this is a diagram. It is a diagram for electric field lines due to an isolated positive charge. The diagram for electric field lines due to isolated positive charge. Similarly, if there is a isolated negative charge, the electric field intensity lines, electric field lines, what will be the direction? Tell me the direction. Tell me the direction. Direction. You have to always draw the direction. Direction. Whether inward or outward. For negative charge. For negative charge, electric field intensity is inward. So this is a diagram for electric field lines. Electric field lines due to a isolated negative charge, and this is a diagram for electric field lines due to a isolated positive charge. That is 8th point. What is that 8th point? Electric field lines are drawn perpendicular to the charged surface. Electric field lines are drawn perpendicular to the charged surface. Understood? Okay, these are some properties of electric field lines, and these properties they will ask many times. Many times they will ask the properties of electric field lines. Here, these are the geometrical representation or pictorial representation of the electric field lines. So, figure number 1. Here, there are two charges, plus Q, plus Q. Both the charges are equal in magnitude. It is plus Q charge is equal to plus Q charge. Both the charges are equal in magnitude and of same nature. Then electric field lines are drawn like this. Electric field lines are drawn like this, and this N will indicate the neutral point. The N will indicate the neutral point. Neutral point. What is a neutral point? A point where the net electric field intensity is 0. A point in the electric field where the net electric field intensity is 0. That point is called as a neutral point. A point where the net electric field intensity is 0, that point is called neutral point. So for two equal and similar charges, the neutral point lies in the midpoint. Neutral point lies at the midpoint of the two charges. That is equal distance from here and equal distance from here. Understood? It is pictorial representation of electric field lines for two equal charges. Here, in the figure number 2, there are two charges. One is plus Q dash, another one is plus Q. And here plus Q dash, that is Q dash charge is smaller than Q. That is this charge is less and this charge is more. Let us say this is plus 5 coulomb. Just for your image, just for your understanding. This is plus 5 coulomb and this is plus 2 coulomb. Hope you understood. Here both are equal. If it is plus 5 coulomb, this is also plus 5 coulomb. If this is plus 2 coulomb, this is also plus 2 coulomb. But here, one of the charge is larger, another charge is smaller. And both are having a same nature charge. Then the neutral point lies near to the smaller charge. The neutral point lies near to the smaller charge. What is neutral point? Did you understood? Okay, once again it will come while solving the numericals. Okay, while solving the numericals, you will solve about the neutral point. What is a neutral point? A point where the net electric field intensity is 0 is called a neutral point. So here neutral point lies midpoint, at the midpoint of the two charges. Here neutral point lies near to the smaller charge. Okay, next, this is electric field intensity due to two equal and opposite charges. This is plus Q charge and this is minus Q charge. For example, this is plus 5 coulomb, then this is minus 5 coulomb. Magnitude is equal, but nature of both the charges are different. This is positive charge, this is negative charge. Understood? This is how the electric field lines are represented. And electric field lines are represented by equidistant parallel lines for a uniform electric field. Here, these lines will indicate uniform electric field intensity. Uniform electric field intensity. Now I will tell you what is uniform electric field. Okay, here I will tell. Okay, uniform electric field. Uniform electric field intensity. A electric field intensity is said to be uniform if the magnitude and direction both are same at the different points. That is, the electric field intensity is said to be uniform if the magnitude of the electric field intensity and the direction of the electric field intensity is same in the at two different points. Then at two different points, the electric field intensity is said to be uniform. That is, if you take this point, the direction of the electric field intensity is like this, and the magnitude here, how much electric field intensity is there, that much amount of electric field intensity is there at the point B. Then the electric field intensity is represented by parallel equidistant lines. These parallel equidistant lines will indicate the uniform electric field intensity. What is the uniform electric field intensity? A uniform electric field intensity. A electric field intensity is said to be uniform if the magnitude and the direction of the electric field intensity is same everywhere. Understood? Direction and magnitude both are same at two different points at different points. Then that electric field intensity is called uniform electric field intensity. And here also two charged plates are there. This is positively charged plate. This is a plate A, and this is a plate B. Are two conductors. It is a one conductor that is positively charged plate, and this is a plate B, negatively charged plate. Then in between these two charged plates, there will be a electric field intensity, and electric field lines will represent, and that electric field intensity will be a uniform electric field intensity, because the electric field lines are equidistant parallel lines. Whenever we have equidistant parallel lines, the electric field intensity will be uniform. And now, what about non-uniform electric field intensity? What is non-uniform electric field intensity? Non-uniform electric field intensity. So, non-uniform electric field intensity means that is either magnitude or direction or both must be different at different points. That is, the electric field intensity is said to be non-uniform, either magnitude or direction or both are different. Then that electric field intensity is said to be non-uniform electric field intensity. And now, in the case of non-uniform electric field intensity, one more character I will write. One more properties of electric field intensity I will tell related to non-uniform electric field intensity. See here. One more, this is quite important. See here, point number 9. These are all 1, 2, 3, 4, 5, 6, 7, 8, and continuation of that another point I will tell. Okay, no problem. Okay. So, the electric field lines are crowded. The electric field lines are crowded in the region of strong electric field. The electric field lines are crowded in the region of strong electric field. And they are spread out. Electric field lines are spread out in the region of weak electric field. See here, this is one of the important properties of the electric field lines. Properties of the electric field lines. What is that property? The electric field lines are crowded. The electric field lines are crowded in the region of strong electric field. And electric field lines are spread out in the region of weak electric field. So let us say we'll draw a diagram like this. So these all are electric field lines, representing electric field lines. Okay. So now here electric field lines are much more crowded. Let us say this has point A and this has point B. And here electric field lines are much more crowded. That means electric field intensity at the point A is larger than, that is stronger then the electric field intensity at the point B. At the point B, electric field lines are spread out. Then electric field intensity at this point will be less. That is ninth point. What is that ninth property? Electric field lines are crowded in the region of strong electric field and they are spread out in the region of weak electric field. Hope you understood. Okay. So did you understood all these diagrams? So these diagrams will indicate, sometimes they will ask the diagrams also. So to draw the diagram of electric field intensity of different charge distribution. Hope you have understood. Okay. So these all are properties of electric field lines. These properties are very, very important. They are asked in the exam many times. Okay. You understood uniform electric field intensity and also non-uniform electric field intensity. Okay. From here, this will indicate uniform electric field intensity. And what about this one? What type of electric field intensity it is overall? Overall, this is a electric field intensity region. Total this region is a uniform electric field intensity region or non-uniform electric field intensity region. It is a non-uniform electric field intensity region because here the magnitude is different, here the magnitude is different. Okay. So that's a pictorial representation for non-uniform electric field intensity, and this is pictorial representation for uniform electric field intensity. Hope you understood all these things. Okay. Many times they have asked in the exam about the electric field lines. So this concept is very, very important. Electric field lines concept is important for the theory exam. So that's why read it properly. Next concept.